All right, is it time? It is time. So here are the things on my mind that people have been talking about. We got U substitution, we got integration by parts, we have the definition of the integral. There's something else somebody asked about. I wrote down somewhere. Did I write it down here? It's right over here. Oh yeah, and then there was this problem. I feel like we did one of these before, but we had something like, um, sure, an initial population rate of change problem. And then let me ask you, has anyone started doing partial fractions yet? So yes, there are some partial fractions. So we'll try to end class with one partial fractions example, but this is the issue with a co-class like this is that we start to get some stratification. Right? Some people are not as far along as other people. So you might be seeing stuff that you haven't gotten to yet, just fine because you're gonna get there. You might be seeing stuff that you already feel like is way behind you, still good to review. So just take it with a grain of salt. Yeah, that's what I feel like that's not the right phrase there, but whatever. Um, just bear in mind that all math is mostly worth seeing. So, we will do that. Sorry, 1 second here. There were a few requests. I'm going to start with this one just because it's fast. So there was this problem, and I'm often going to kind of fudge the numbers because the numbers for this problem were especially gross. It was a Weber problem where you're given something like an initial population of 900. And then we're told that the rate of change is something like 950 is actually a much worse number. 950 e to the 1.2 t. It was actually something like 948 point blah 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 e to the 1.10 grossness t. And then we're asked to find the population 2 hours later. So this is another example of an initial condition problem where you're really being asked to solve using an antiderivative. It's just phrased in a very different way. I could have just easily said, find the antiderivative of 950 e to the 1.2 t, given that at time equal to 0, the population is 950. Sorry, 900, apologies. So here's what I'm thinking. And I believe they called this the rate of change of R of t. So here's what I'm going to write down first. The rate of change of R of t. dRdt is another name for that. And dRdt is equal to 950 e to the 1.2 t. And then we're going to solve for the function R by anti-differentiating both sides of this equation. The antiderivative of the derivative is just your function. I could use more fancy notation, right? I could be like, I could separate variables and say dr equals 950 e to the 1.2 t dt, and then integrate both sides. Wow, that's a 9, James? Sure. And then integrate both sides to get r on the left or r of t. And that's not where you put that symbol. Sorry. I mean, some people do actually, but not me. And then on the other side, the antiderivative of 950 e to the 1.2 t is 950 e to the 1.2 t divided by everybody. Thank you. Yes. Where did I hide? Yeah, I'm like, where did I have my water from myself? So exactly 1.2. And then plus c. And then the rest of this is not too terrible. We're going to plug in the fact that at t equals 0, the population is 900. So we're going to say that r of 0 is equal to 950 e to the 0 divided by 1.2 plus c. And that should equal 900. Then we're going to solve for c. So c is going to equal 900 minus this number, which is just 950 divided by 1.2. You could use a calculator, or you could just leave it as is. And then to finally get r, so we have now that r of t equals this gross function, 950 over 1.2 times e to the 1.2 t plus this gross c number, 900 minus 950 over 1.2. And then to answer the actual question that was asked, which is to find the population 2 hours later, we're just going to plug in 2 for t and get r of 2 equal to this. Yeah, this is the right answer. 950 over 1.2 times e to the 1.2 times 2, which is 2.4, plus this trash over here. And then you throw that all into a calculator and get some disgusting answer. It's kind of just gross. I don't know why WebWork likes to give you such awful numbers sometimes, but it does. So such is life. All right, that one's not too terrible. Okay, we can do that one. So hopefully the last definition of the integral question I ever show you, doesn't have to be, but hopefully, really my hope is that your class will move on and start doing other stuff because the definition of the integral gets to be a bit tedious, but we'll do one more because I do think they are worth seeing the thing one more time. So we've got the integral from 1 to 2 of x cubed dx, and we're asked to use the limit definition of the integral. So when I'm doing this, I'm going to just identify the pieces first. I guess I can number things here. And then write out the limit definition. Actually, backwards. Write the limit definition first. So its limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I times delta x. And then I would probably write down 3 things. First, what delta x is in a second. Then what x sub I is. And then what f of x sub I is. So the general formula for delta x, b minus a over n, which in this case is 2 minus 1 over n, which is 1 over n. X sub I, the general formula is a plus I times delta x, which in this case is going to be 1 plus I times 1 over n. And I would probably write that slightly more simply as just 1 plus I over n. Whatever we have here, like if it's I times 3 over n, we usually write it as 3I over n. We don't usually leave the I out in front. And then finally, f of x sub I, I'm just going to take this 1 plus I over n and plug it into what's my function? Right, the function is the thing that you're integrating. So right there, that is your f of x. So f of x is x cubed. F of x sub I is 1 plus I over n cubed. Now you have to multiply that out. So unfair. Well, not really if you know a cool trick. So, another piece of paper for a cool trick real quick. We'll come back to this, I promise you. Cool trick for multiplying out something plus something to a power. You might have seen this before. You might not have. There's this wonderful thing called Pascal's triangle, which goes on and on and on forever and ever and ever. And there's some really cool patterns in it. One of the patterns that's in it is that these numbers here are the coefficients of the oh my gosh, of the binomial expansion. So like if I wrote out x plus y to the 0th power, I would get 1. Okay, not that exciting yet. X plus y to the first is 1x plus 1y. X plus y squared is 1x squared plus 2x to the first, y to the first, plus 1y squared. And the pattern continues. X plus y cubed is 1x cubed, and then it's 3x to the 1 less power, y to the 1 more power, plus 3x to the 1 less power, y to the 1 more power, plus 1x to the 1 less power, y to the 1 more power. And it just goes on and on and on and on. So if you want to do x plus y to the 4th, it would be 1x to the 4th plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus 1y to the 4th. Then what we're going to do is we're going to use this third row. Yes, it's the third row because this is the 0th row to multiply out. Oh, paper's on the floor. I'll get it later. To multiply out 1 plus I over n cubed. That's going to be 1 times my first thing cubed, so just 1 cubed, plus 3 times 1 squared times I over n, plus 3 times 1 times I over n squared, plus I over n cubed. This is definitely a pattern you probably should know. Comes up often enough that like you should know that, oh yeah, something plus something cubed is 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. So then, writing this out, going to be the limit as n goes to infinity of the sum from I equals 1 to n of all this garbage, I might just write 1 plus I over n cubed for the moment here, times 1 over n. I typically like to simplify this, writing the limit and the summation every step. You might not want to do that. So if we're just going to write out what f of x sub I times delta x is, and simplify it, it's going to be all of this times my delta x. So it's going to be, let's simplify this as we go here. 1 plus 3 times I over n plus 3 times I squared over n squared plus I cubed over n cubed, all times 1 over n. And so then we can say that our limit definition is going to be the limit as n goes to infinity of the sum from I equals 1 to n. Multiplying this through, we're going to get a 1 over n plus 3i over n squared plus 3i squared over n cubed plus I cubed over n to the fourth. And we see that lovely pattern that I always like to look for, which is that every power of n is 1 larger than every corresponding power of I. If you don't see that, you've probably made a mistake if you're doing this kind of problem. Break it up into 4 pieces. I'm going to do the breaking up like this. 1 over n times the sum of 1 plus 3 over n squared times the sum of I plus 3 over n cubed times the sum of I squared plus 1 over n to the fourth times the sum of I cubed. Yes, I got a little lazy there and didn't write I equals 1 to n on each of them. Your teacher would probably forgive you for that. Maybe not, though. I don't know. Some people are real sticklers. Now's where we throw in the formulas for each of those summations. So it's going to be 1 over n times the sum from I equals 1 to n of 1 is n. And the sum from I equals 1 to n of I is n times n plus 1 over 2. And the sum from, 3 over n cubed times the sum from I equals 1 to n of I squared is n times n plus 1 times 2n plus 1 over 6. And finally, the last one, 1 over n to the fourth times the sum of I cubed is that one squared, n times n plus 1 over 2 squared. Then we try to show us, I don't know, I want to say as little work as possible, but so this is going to be 1. This is looking like 3n squared plus lesser terms over 2n squared. So that's going to give me a 3 halves. This is looking like 3 times n times n times 2n. So a 6n cubed plus smaller terms over a 6n cubed. So it's going to be a 6 over 6. And then we have a we have an n to the fourth on top over a 4n to the fourth on the bottom, because that 2 is getting squared. So we have a 1/4. And then we add it all up. Our common denominator is 12. 12 over 12 plus this 18 over 12. I feel real dicey about this, but whatever. 12 over 12 plus 3 over 12. So we're getting 30, 45 over 12, which reduces to, divide by 3, 15 over 4. And if you wanted to make yourself crazy, you could then go check to see if your answer's right. Or you could just go with the fact that you did enough work and it looks pretty good, that if it was off by a little bit, you shouldn't waste your time on the test trying to see if this is right. Is it right? I hope so. Let's see. If I did this the other way, I know I'm going to make myself crazy, but that's all right. I get x to the fourth over 4, evaluated from 1 to 2. So I get 2 to the fourth over 4 minus 1 to the fourth over 4. Yes, it's right. Thank goodness. Oh my God. I'm really unhappy if it was wrong. Okay. Kind of a lot there, right? That question is definitely, to me, when I saw it, I was like, oh, that doesn't look too bad. I kind of forgot about the fact that we were starting at 1. And so that when we had our x sub I, which is 1 plus I over n, keeping that out was going to be kind of gross. And you're getting a term with each power. And so you have to know all the formulas to do that problem. It's a good question, but it's kind of a pain in the butt. All right. Time's a wasting. Let's do these other 2 problems. I'm going to switch. Oh, that one's terrible. We'll get to that second one in a minute here. Let me pick up this piece of drop paper before I forget about it. But don't forget about it. All right. But yeah, let's look at this other one, because this other one does have something to offer us. Why do I have all my papers over here? It should be over here. Yeah, let's make that more interesting. Let's say we want to find the integral of x, squared times the 5th root of x minus 4. Similar enough. So this problem doesn't look great. X cubed. No, I don't want to make that. Let's make it x squared. X cubed is just cruel. Sorry about that. This has one of the two hallmarks of a U substitution. I have something stuck inside another function. It also, to me, does not look like integration by parts. That's not entirely true. You probably could tackle this one with integration by parts, but it's probably gross. U sub is usually the better choice to go if you're not sure what to do first. Also, it's missing one of my integration by parts hallmarks. It's not a mixture. I don't have anything other than x to a power. I don't have a trig. I don't have an exponential. I don't have a logarithm. So it's missing one of the usual things I look for if I'm going to try and do integration by parts. There are some problems that don't meet all the hallmarks that you can do it for, but this way is better. So I'm still going to try a U sub. I'm going to let U be the stuff that's inside there. And I guess technically we're not missing the other hallmark in that my derivative, which is just equal to 1, so du is 1 times dx, technically that's also there. The issue, though, is that I really would have liked it if this had been like an x cubed minus 4, and then my derivative would have been something x squared. Because when I start replacing things, I have a leftover x squared, which is not ideal. And my dx is du, my x minus 4 is u, this pen is dying. I mean, I'll still keep it and then try to use it later, but okay, much better. Okay, so we've got these leftover x squared, and what we're going to do is what's called a back substitution. So when you have a leftover x, but everything else is kind of worked, or x to a power, and everything else is kind of worked out okay, we take our choice for u and we solve for x. So I'm going to add 4 to both sides and say that x is equal to u plus 4. I'm going to rewrite this as the integral of u plus 4. I should have picked a different number. My u's and my 4's look too similar. Squared times the 5th root of u. And then you have to multiply it all out. So we're going to multiply it out. We're going to get u squared plus 8u plus 16, all multiplied by u to the 1/5 power. We're going to distribute the u to the 1/5 to each term. So 2 plus 1/5 is 11/5. 1 plus 1/5 is 6/5, and 16 u to the 1/5 power. Then we apply the anti-power rule to each of these three terms, and we're going to get u to the 11/5 plus 5/5 is 16/5 times 5/16 plus 8 times a number times u to the 11/5 times 5/11 plus 16 times a number times u to the 6/5 times 5/6 plus c. That is ugly. So then we finish it off by plugging back in what u is equal to. So we get 5/16 times x minus 4 to the terrible 16 over 5. 8 times 5 is 40 over 11 times x minus 4 to the 11 over 5 plus 16 times 5 is 80 over 6 reduces to 40 over 3 times x minus 4 to the 6 over 5 plus c. Ugh. I mean, I've seen worse. Lots worse, like that other one over there. All right. Okay, so let's talk a bit more about integration by parts. We ended the last class kind of briefly talking about tabular integration, which I think is a great method. Again, it only really works for 3 types of integrals. E to the x times x to a power, sine of x times x to a power, or cosine of x times x to a power. It only really works if your choice for dv is something that will survive repeated integration without getting terrible. Only e to the x, sine of x, and cosine x, you can easily anti-differentiate over and over and over again and not have them get extra awful. So with that in mind, sorry, keeping track of where I put things. How would we integrate something terrible like x cubed times e to the 5x? Well, here's what I don't want to do. I don't want to do integration by parts 3 times. We could, it's doable, but the faster, easier way to do this is to make a table, to do tabular integration. Making the typical choices of u and dv. So if I was looking at just this integral and thinking integration by parts, I would pick my u equal to x cubed. and my dv equal to the rest. Taking the derivative of u, it does get simpler because the derivative of x cubed is 3x squared. That's to a lesser power. We consider that to be a simpler thing. The antiderivative of e to the 5x essentially does not change. It's going to be e to the 5x divided by 5. So our dv shouldn't get more complicated when we antidifferentiate it. Our u should hopefully get simpler. So we're going to make columns. We're going to start off with u here, and then we're going to take every derivative until we get to 0. So 3x squared, 6x, 6, and yes, we should write 0 because that tells us how many columns or rows we're going to need for the other column. So our dv was e to the 5x. The antiderivative is e to the 5x divided by 5. The antiderivative of that is e to the 5x divided by 25. The antiderivative of that is e to the 5x divided by 5 cubed. The antiderivative of that is e to the 5x divided by 5 to the 4th. Yes, we need all of them. And then we're almost done. We're just going to take the positive product of those things, the negative product of those things, the positive product of those things, and the negative product of those things. So our final answer here should be x cubed times e to the 5x over 5 minus 3x squared times e to the 5x over 25 plus 6x times e to the 5x over 125 minus 6 e to the 5x over 625 plus c. Still not great, but certainly less awful than actually doing this process 3 times and going through every kind of step. Not every repeated integration problem is quite so fortunate. Like this next one, for example. Oh, where are those? Yeah. I don't really want to see them. Sure. So let's look at the next problem. Something like, sure, we'll go slightly unclassic here. Let's start with the integral of e to the 2x cosine of x. Yeah. All right. So typically, I would start here with integration by parts, which is the right thing to do. I see a mixture. I don't see a good u sub choice, right? I see e to the 2x times cosine of x. Letting u equal 2x isn't going to get me anywhere for a u sub. So I'm going to pick part of this to be u and part of this to be dv. And normally I would pick my u to be the trig thing and my dv to be the exponential thing because of the LATE acronym. Technically, in this example, you can go the other way and it'll still work out fine. So either way, it's fine as long as you make the same choice both times. So I'm going to pick, I'm not doing tabular here, right? This is not a tabular one. I don't have x to a power. So I'm going to pick my u equal to cosine of x, my dv equal to e to the 2x dx. My du, the derivative of cosine is negative sine of x. Multiply that by dx. My v is the antiderivative of e to the 2x, which is e to the 2x divided by 2. Plug that all into our integration by parts formula. So we have the integral, and I will write this out here, of our, sure, James, of our u times our dv equal to our u times our v. So cosine of x times e to the 2x divided by 2, minus the integral of our v times our du, our e to the 2x over 2 times negative sine of x dx. And before we start doing integration by parts again, which we're going to do, I would recommend simplifying this just a little bit to make it look a little less gross, specifically the integral part here. So I would rewrite this as 1/2 cosine of x times e to the 2x. Minus a minus is plus, and I'd bring out the 1/2 coefficient. So 1/2 the integral of e to the 2x sine of x dx. And now we have to do integration by parts again. And what we're going to do is we're going to make the same kind of choice, meaning in the first iteration, we chose u to be the trig thing and dv to be the exponential thing. In the second iteration, we have to make the same choice. U is going to have to be the trig thing. dv is going to have to be the exponential thing. If we make the opposite choice, what will happen is we'll actually undo the work we just did and end up getting that the integral of e to the 2x cosine of x dx is equal to the integral of e to the 2x cosine x dx, which is true, but not helpful. You just get back where you started. So same choices, let's use different colors. So now for this one here, we're going to let u equal, again, the trig thing. And dv is e to the 2x dx. Your du is going to be cosine of x dx. And your v, again, is going to be e to the 2x divided by 2. So now we're going to get that, and I'm writing this on the left here for an actual reason. I'm not just writing it for fun. I'm going to get that the integral of e to the 2x cosine of x dx is equal to 1/2 cosine x, e to the 2x. Plus, now notice there's a 1/2 out here. That 1/2 is going to multiply by the entirety of my uv minus the integral of v du. It's going to be 1/2 times my u times my v, which I'm going to write as 1/2 sine of x times e to the 2x, minus the integral of my v times my du, which is e to the 2x over 2 times cosine of x dx. And that 1/2 has to multiply both pieces of that bracket. Okay, the rest of this is just a little bit of algebra. So we have the integral of e to the 2x cosine of x dx equal to 1/2 cosine of x e to the 2x. 1/2 times 1/2 is 1/4 sine of x e to the 2x. And then 1/2 times a negative 1/2 is minus 1/4 integral of e to the 2x cosine of x dx. Oh, look, I ended up getting the same integral I started with. And instead of just repeating this process forever and ever, I'm going to take this and add it over to the other side of this equation. So I'm going to add 1/4 of this integral to both sides. Which always feels like you're kind of just cheating. Like, I feel like I just did this thing twice and then magically the integral is going to come out. It is the right answer, but it always feels like I didn't actually anti-differentiate it for real, but I did. So what I end up getting here is I get 1 of a thing plus 1/4 of a thing is 5/4 of that thing. So we have 5/4 times the integral of e to the 2x cosine of x dx equal to, I would probably factor out the e to the 2, no, fine. 1/2 cosine of x times e to the 2x plus 1/4 sine of x times e to the 2x. And then finally, we multiply both sides by 4/5 to end up getting that our integral of e to the 2x cosine of x dx is equal to 4/5 times all of that. 1/2 cosine of x e to the 2x plus 1/4 sine of x e to the 2x plus c. Kind of gnarly. That is a very standard type of question. That's all. That statement should end with a period. That is a very standard type of question where you're asked to integrate something like e to the x times cosine of x, or e to the 3x times sine of x, or something where it's an e to the multiple of x times a sine or a cosine of a multiple of x. And this is always the process. Integration by parts twice. You get back to where you started, you add it over to the other side, you divide by the coefficient or multiply by the reciprocal, and that's your answer. So let's look at this gnarly thing. Yeah. Yeah. The integral of, man, do I really want this? Yeah. Sure, I'm going to change it up a tiny bit. I'm going to make it cosine of, I don't love that, the natural log of x to the 6th. Okay. So before you do anything here, I think you should rewrite the natural log of x to the 6th as 6 times natural log of x. There are two ways to go about doing this problem. And to me, they both feel terrible. One of them would be to start with a U substitution, where I might have actually made the wrong choice by simplifying this that way. Fine. I might start with U equal to 6 natural log of X. Trying a U sub here. Okay, but if I find du, I'm going to be disappointed. My du is 6 times 1 over x dx, and I definitely do not have a 1 over x times dx in my integral. When that's the case, but I still think my u sub might be the right choice, there's a couple things you can do. It's actually the same thing, it's just a couple different ways of doing it. You want to figure out what dx is equal to. You could solve for dx here. That is not my preferred way of doing it, but you could say, well, dx equals x times du divided by 6. But if I plug that in over here or over here, I'm not going to be able to cancel this x out, which is usually what we're trying to do when we do it that way. So then we would kind of say, well, if you solve for x here, then x is going to equal e to the u over 6. That's a e to the u over 6. So this dx is actually equal to e to the u over 6 times du over 6. That is not the best way to do it, in my opinion. The better way to do this is to find x right here and say that this is just x like we did, and then just take the derivative of both sides. The derivative of x is just going to give us dx. The derivative of e to the stuff is e to the stuff times the derivative of the stuff, of the du. Either way, you're getting to the same place. Kind of weird. But this is what's called, what is this called typically? It's called like a power substitution, where you make your u choice, but then like the du dx thing isn't working out. So you solve for x and then take the derivative of that instead. So we solve for x and we took the derivative of both sides. So checking this out, we're going to get cosine of u. And then we're going to get e to the u over 6 times 1/6 times du. And oh, wouldn't you know it? That looks a lot like the integral we just did. Not exactly like, but essentially the same idea. E to the something, a multiple of your coefficient, times cosine of your, e to the multiple of your variable times cosine of your variable. So you can start with a u sub there, and then you're going to be stuck with this double integration by parts problem where you end up with the same thing you start with. When that happens, when you do a u sub and you see that you get to a place where you're going to get some sort of terrible integration by parts twice, you probably could have made a different choice for your integration by parts in general. So what you could do here, instead of starting with the u sub, which I recommend, is instead making a bigger choice. Say, well, I'm going to try this one. By doing integration by parts. And there's only one way to do it using integration by parts. I don't have anything really multiplied here. I don't have cosine times natural log of x to the 6, or as I was writing before, cosine of 6 times natural log of x. Sorry about that. That's not multiplication, that's composition. The only multiplication that's happening here is cosine of 6 natural log of x times dx. But that's enough. We can try integration by parts by letting u equal to essentially the entire integrand. And my dv is just a lonely dx. Let's take the derivative. My du is going to equal, okay, the derivative cosine is negative sine of my stuff, the negative sine of 6 natural log of x, times the derivative of 6 natural log of x, which is 6 over x dx. And my v is the antiderivative dx, which is x. Now watch what happens when we put it all together. This is going to be equaling the u times v. So u times v, I'm going to say that's x times cosine of 6 natural log of x minus the integral of v times du, x times negative sine of 6 natural log of x times 6 over x dx. And very, very fortunately here, the x here and the x here cancel. So then we're going to end up with an integral that looks very, very similar to the integral that we started with. Minus minus is plus, bring out the 6. You've got a sine of 6 natural log of x. Now you do it all again. So now we're going to look at this. We're going to say, oh, we're going to make the same sort of choice. We're going to let u equal sine of 6 natural log of x. My dv is still going to be dx. My du is the derivative of this, which is cosine of 6 natural log of x times 1 over x times 6, or just 6 over x dx. And my v is x once again. So now we end up getting x times cosine of 6 natural log of x plus 6 times the integral. Nope, not times the integral, times bracket uv minus the integral of v du. There's my uv, x times sine of 6 natural log of x minus the integral of v du, x times cosine of 6 natural log of x times 6 over x. dx. The x's cancel again. And now here's the terribleness we've got. We've got the integral of cosine of the natural log of 6 natural log of x. And it's equal to all of this. X cosine of 6 natural log of x plus 6x times sine of 6 natural log of x. And then the 6 times the 6 is going to be a minus 36, is a minus sign there, times the integral of cosine of 6 natural log of x. And then you would add 36 integral of cosine of 6 natural log of x to both sides. You would get 37 times the integral of cosine of 6 natural log of x equal to this same stuff. And then you would divide both sides by 37 to get that the integral of cosine of 6 natural log of x dx is equal to 1/37 times x cosine of 6 natural log of x plus 6x sine of 6 natural log of x. Plus c. It's all wrong if you don't have the plus c. It's mostly right if you don't have the plus c, but you need the plus c. WebWork wants that plus c. Good Lord, that's a lot, right? So if you see something that looks gross like this, you kind of just have to try stuff. And usually the stuff you have to try is either a U sub or integration by parts. Speaking of which, yeah. So one more. So many examples to do. Let's look at another example real quick here. Let's say I want to do the integral of e to the square root of x dx. This is another example of I don't see a lot of choices. The only choice I really see, I guess I have choices here. I could either do a u sub, letting u equal the square root of x, or I could try integration by parts, letting u equal the e to the square root of x and dv being dx. If I'm not sure which way to go, I'm always going to try u sub over integration by parts. It's usually the easier choice. And I would encourage you to take that to heart. U sub should be your default. I don't know what else to try. Try u sub. So we're going to try u equal to the square root of x. And then the derivative of that, and I do think it's worth memorizing that although you can write this as 1/2 x to the negative 1/2 dx, I would encourage you to memorize it as 1/2 times the square root of x dx. I'm sad though, because I don't have a 1/√x in my integral. So I would encourage you to go this way. If you don't see this, then go back over here and solve for x. So we're going to get u squared equal to x, and then differentiate both sides. What's the derivative of u squared? 2u. What's the derivative of x? 1. Slap on the appropriate d whatevers. A du on the u side, a dx on the x side. And now we're going to rewrite our integral. Dx turns into 2 times u times du. And e to the root x becomes e to the u. And now this looks like an integration by parts problem. I've got essentially x times e to the x, or if you like, 2 times the integral of u e to the u. And I always feel bad when I get to this point of the problem. I'm like, it's integration by parts, but I've already used the letter u. I don't want to call u equal to something else. So you can either go back and you can change u to like another letter, like t is what I have to do. Or instead of using u and v, you can use w and v. So we're going to do integration by parts, but we're going to use w instead of u. So we're going to say that the integral of w dv is equal to wv minus the integral of v dw. So same idea though. We're still picking w to be the algebraic thing and dv to be the exponential thing. So here, w is going to equal u. dv is going to be u. Derivative, the derivative of w is 1 dw. The derivative of u is 1 du. Antiderivative of, oh my gosh, antiderivative of dv is v. Antiderivative of e to the u is e to the u. So we're going to rewrite this as 2 times our w times our v, but we're not going to write w times v. We're going to write u times e to the u. Just like we don't write u times v, we write x, right? Whatever the x thing is times whatever the x thing is. Minus the integral of v du is the integral of e to the, sorry, v dw, which is equal to e to the u times du. I know it's a little weird. And then we're going to replace our u's with what they're equal to. So we're going to get 2 times the square root of x times, oops, I'm not done yet, James, hold your horses. Can't start replacing things until you've finished integrating, which I haven't. I still have an integral of e to the u. So I should write this as 2u e to the u minus 2 times the integral of e to the u, which is also e to the u. Let's see. And now I can start replacing things. And say it's 2 root x e to the root x minus 2 e to the root x plus c. Kind of weird looking. I mean, they're all kind of weird looking at this point, I feel like. Okay, yeah, sorry, partial fraction is not going to happen today. In 6 minutes, definitely not. What I should do is I should do an example of that. Where'd you go? Sorry. I want the nice one. There we go. Yes, let's look at this integral here. So let's look at the integral from 0 to 4 of x over the square root of 9 plus x squared. So we haven't done a whole lot of definite integral examples, but the only difference really is that you're going to do the antiderivative and then you're going to plug in your top limit first to subtract and plug your bottom limit in second. Always top first, bottom second. Top first, bottom second. Top first, bottom second. Top first, bottom second. Okay. So the issue here is that we can't just antidifferentiate that directly. We have to do one of our methods, and it's probably a u substitution. So we're going to do a u sub. I think there's an obvious choice. U should be 9 plus x squared. Our du is going to be 2x times dx. And I would say 1/2 du is equal to x times dx. So now I'm going to rewrite this in the language of u. And you have a couple choices here. So just not worrying about my limits of integration for a moment. Dx is going to be 1/2 du. And I have, sorry, x dx. Ooh, x dx is getting replaced by 1/2 du. And then I'm left with a 1 over the square root of u. And you have options. I would say there's 2 reasonable options that I would say are good. There's other less good options that I don't recommend. Yeah, okay. So one option is to not change your limits of integration, but you have to let the person grading your work know that you know what you're doing. So you're like, you can't just write 0 and 4 here, because they're going to think you mean u is 0 and u is 4. But u isn't 0. U is, well, I don't know yet. X is 0 and x is 1. So one option is to leave this as x equals 0, x equals 4. Proceed along your merry way, antidifferentiate, get the antiderivative, plug back in what u is equal to in terms of x, and be fine. Fine, we can do it that way. Let's do it that way. We'll do it both ways. That's going to be 1/2 the integral from x equals 0 to x equals 4. You do need to write the x equals every step, in my opinion. U to the negative 1/2 du. And then we antidifferentiate. We get 1/2. The antiderivative of u to the negative 1/2 is u to the positive 1/2 divided by positive 1/2. Normally I would say multiply by 2, but I'm just going to point out here that the 1/2 divided by the 1/2 is just 1. From x equals 0 to x equals 4. That's going to be the square root of u, which is the square root of 9 plus x squared from x equals 0 to x equals 4. And then you can plug in and get the square root of 9 plus 4 squared minus the square root of 9 plus 0 squared, which is the square root of 25 minus the square root of 9, which is 2. This is not my preferred way of doing it, but it's fine. I think the better way that requires a little bit less writing is to instead change your limits of integration to the corresponding u values. So I would like to write this as 1/2 the integral of 1 over the square root of u du, but knowing that, I got a million pens here, sorry. Knowing that x equals 0 and u is equal to 9 plus x squared, u is going to be 9 plus 0 squared, which is 9. And if x is equal to 4, u is going to be 9 plus 4 squared, which is 25. And then you don't have to write x equals or u equals. It's implied that it's u there if you don't write anything. So then you can just go along. You can say it's 1/2 the integral from 9 to 25 of u to the negative 1/2 to u. You can anti-differentiate. You get 1/2 times u to the positive 1/2 times 2 over 1 this time, just to change it up from 9 to 25. That's going to be, those cancel, the square root of u evaluated from 9 to 25. And then you just plug in. You never have to change back. In fact, it is wrong to change back. And either way, you get the same answer. So if it were up to me, 99 times out of 100, I would encourage you to do it this second way, where you change your limits of integration. Sometimes it's not beneficial to do that. There are some small cases where it's terrible to change them. But most of the time, you're going to have to do that work anyway. Whether you're changing them here or up here, when you plug in your u squared, you're going to get 9 plus u squared, right? Either way, you're still doing that arithmetic somewhere. So yeah, I would recommend changing. What can I squeeze in a minute and a half here? Oh yeah, I should do one of those. Yeah, okay. Someone else, sorry, going back to a little bit here. We'll do one more. Fundamental theorem of calculus part 1. So if your g of x is equal to the integral of, let's make it exciting, 3 natural log of x to 4 of cosine of t squared dt, what's g prime of x? I will remind you every time, probably. The point of this problem is not to try and do anything long. The point of this problem is to know what the fundamental theorem says and just get the answer, right? This is one of the few times I would say you're encouraged to not show any work here. And this one you actually really can't, right? You cannot integrate cosine of t squared, literally, not possible. Can't do it. So we know the idea here is that you're going to plug in your variable thing wherever you see t, and then if your variable thing is more complicated than just x, you have to multiply by its derivative because of the chain rule. So we're going to get negative, because it's in the bottom limit, cosine of 3 natural log of x quantity squared. Not 3 natural log of x, not the cosine itself, sorry. And then we have to multiply by the derivative of 3 natural log of x, which is 3 times 1 over x. That's the whole story. There's nothing else to say there.